In this lesson, we're going to learn about energy, forms of energy, the principle of conservation of energy, energy flow diagrams, and energy efficiency. Lots of energy. Let's begin. What is energy? Energy is a scalar quantity, and it is abstract. You can't always perceive it. The definition for energy is that it is the ability to do any form of work. It's a little confusing when you think of it like this, but look at the next sentence. It's like the currency to do work. For example, money. Money is the currency to shop. So if you want to do work, you have to have a certain amount of energy. And we use joules as our unit of measurement for energy. The joule, denoted by a J, a large J, it is the unit of energy that is required when a force of 1 Newton moves an object 1 meter. 1 joule equals 1 Newton meter. 1 Newton meter equals 1 meter squared kilogram seconds squared, per second squared. 1 joule is very small. Because of this, you will probably become more accustomed to using larger forms or to the powers of 10, and most likely probably 10 to the 6th joules, which is equivalent to a megajoule, or the gigajoule, which is 10 to the 9th power. There are many different forms of energy, and they fall into one of two categories. The first category is kinetic energy, denoted as Ke, and it is the energy of movement. Anything of motion belongs into kinetic energy. The second category is potential energy, Pe, and it is stored energy due to its position. We will go over each of these in a little bit. Some energy forms can be just potential energy, some can have kinetic energy, and some are both potential and kinetic. Mechanical energy involves the motion or position of an object. It can be either potential and or kinetic. So here are some examples. For kinetic energy, and it is just purely movement, for example, a frog jumping, or sound. And sound is, for example, any kind of sound that comes from either an animal making a call, or it could be something as dropping a pencil, and that sound that is produced creates waves, and that is kinetic energy. For potential energy, a few examples is a parked car. It has the potential to move, therefore it has energy that is not in motion but could be. At the top of a slide is another example of potential energy. One example of something that is both kinetic and potential is a moving baseball, or any object that has a high speed, which is the kinetic, and its vertical position, which means that it has the potential to have more energy. So the vertical position above the ground would give it more possibilities for energy. Here are some pictures, and this is just for kinetic. So remember how I mentioned that any sound that you make creates waves, and those waves produce energy. Over here you have mechanical energy that is kinetic also with the person that is just running. So any motion is kinetic energy. Example again with the molecules of water rushing over or down a river. This is kinetic energy. An avalanche that is in motion, that is kinetic energy. Moving objects, again, it does not have to be a live human being or an animal. It could also be moving vehicles. For potential energy, here, remember we said it was due to its position. So for example, we had the avalanche. Before the avalanche becomes kinetic, it is potential. So here's a snow mass of where possibly the snow could break off and then become kinetic. Here's a balanced rock where if the rock tilts, it could fall, which then it could become kinetic. But right now, it's potential. Same thing up here with the cars at the top. This is the same as if a person was at the top of a slide. It has potential energy, which could then turn into kinetic. And again, with the book being up on the shelf, it could have potential energy as it rushes down, turning into kinetic. alongside with this example here of the weightlifter, and he is holding the bars up above his head, and when he drops the bars or when he lowers the bars, there would be energy there. Mechanical energy that is both kinetic and potential. Remember that ball that's flying in the air? While it's flying, it has the velocity, just like the dog that's flying in the air, but and then it also has the potential energy because it is experiencing the downward fall. So because it is higher up in elevation, its vertical position is higher, therefore it has potential energy. Thermal energy is a form of kinetic energy, and it talks about the energy that is moving in the moving parts of the atom and the movement of the atoms themselves. And we know how atoms can move, right? So as atoms move faster, that creates more energy, and it is in the form of thermal energy. And as atoms move faster, then that increases, and objects begin to feel warm or hot. It can also go the other way, where there is a loss of thermal energy in exothermic and endothermic reactions, right? So that is thermal energy. Some examples: boiling water, melting ice, hot pavement, burning wood. Here are the molecules of a solid, and here they are as a liquid going to gas and then plasma. As you move across from solid to liquid, gas, and plasma, these are the states of matter. You are increasing the energy, therefore the molecules are moving around more. As you have more activity, you have more thermal energy that is being released. Over here we have heat being released from the pouring of the hot water, which is then warming up the mug. Here we have ice melting, we have water boiling, we have fire burning, which is releasing the heat from the interaction between the fire and the wood. And then over here, this is actually really cool, the sun on the pavement causes the atoms in the pavement to move around a lot, right? And so because the atoms in the pavement are moving around, it releases heat, and it creates heat waves. And so this is another form of thermal energy. Electrical energy is a kinetic energy. It is the movement of the electrical charges, and those can be either positive or negative, and this produces energy. Some examples are when batteries are working, power lines, lightning, anything that uses electricity, anything that allows electric charges to travel is going to be a form of electric energy. Here are some pictures. And one of the things to note here is that electrons are moving here from the battery and then going over into the light bulb, which is then turning on the lamp. So this electricity is a flow of electrons, and this flow is why it's kinetic energy, and this creates electric energy. And these are all in the forms here, as well as, sadly, this person here who is going to be executed. And then, of course, we do have natural sources here caused by nature, such as lightning. Chemical energy. Chemical energy is potential energy. It is stored energy. It is located in the bonds that hold the chemicals together. So if you've heard of compounds, that when you break those bonds, it creates energy. Some examples are energy that's stored in the food that we eat. So every time we eat, we are breaking bonds that release energy so that we can use it, turn it into chemical energy that we can then use for survival. When we drink water, so for example, the water that we drink, we break the bonds and then it becomes energy. Matches before they make fire, this is a form of chemical energy that is potential. So here are some examples. So this is what I was talking about. Here is a molecule of glucose, and when you break the bonds, then it releases the energy that's inside of it. When you eat the food, whatever the bonds or the compounds that you're eating, such as possibly they have glucose, carbohydrates, those bonds are going to break and they create chemical energy. Same thing here with the piece of coal. When you have the coal, it is sitting there. It has potential to do work. It has potential to be to make energy, but it's just stuck there in that piece of coal until, of course, you burn it, or the oil when you burn it. And of course, here we have an example of a match, and the match head has a few different elements and compounds. So, for example, there's sulfur, there's phosphorus, there's potassium chlorate, ammonium phosphate, and so that is just sitting there until you use it. So therefore, it is chemical, it's potential energy. Of course, when you strike the match, it breaks the bonds and it releases the chemical energy. Electrochemical energy is kinetic. It is energy of movement of light and other electromagnetic waves. The movement itself of the waves causes the energy. And this example is of visible light and all different rays. So we have X-rays, gamma rays, ultraviolet rays, infrared rays, all different kinds. Here is an example. Here is where visible light, this is what we can see from red to violet. However, outside of that, we have radio waves, infrared, which is up here where it's actually showing your thermal heat of this parrot, for example. Here we have UV rays, X-rays, gamma rays, and then, of course, there's microwaves over here. This is an example up here of the forest with the visible light that we see. And over here we have a laser. All these are examples of light energy. Elastic energy, also known as strain, is a potential energy. It is stored as a result of stretching or compressing or deforming something. For example, rubber bands have stretch. Bungee cords, trampolines, springs, an arrow drawn into a bow. So when you're pulling back on the arrow or pulling back on the bow, this is stored energy. Here are some examples of what we had mentioned before. So when you pull this back, it has the potential to do work, just as much as this bungee cord over here with this person falling. We also have the bed right here, or mattresses. Whenever you sit down, you have the potential of potential energy of elastic energy. Okay, and then you have your trampoline over here. Gravitational energy, also known as gravitational potential energy, denoted as GPE, is obviously a potential energy. It is the energy that is caused by its vertical position or height. Some examples are a pendulum, when the ball is pulled back or pulled up, and it is before you let it go. So it is a potential energy of stored energy if you were to let go and release that ball. A wrecking ball of a demolition machine is also another example of potential energy. The person at the top of a slide. Here are some pictures of examples. And we mentioned the wrecking ball. So here is the potential energy when the ball is pulled back before it swings and becomes kinetic. Down here we have the pendulum, and if you have the pendulum pulled back, what you'll notice is that it shifts from potential energy down to kinetic and goes back up to potential energy. And so it cycles through potential and kinetic. The girl up here holding the ball at a certain height, so there's a cliff, when she releases the ball, it will become kinetic, but before that, as she's holding it here, it has the potential to do work. Therefore, it is gravitational potential energy because gravity would be helping to pull that object down. Here is another example with a cyclist who is going up a hill. When this person is up at the top and before they're going to come back down, there is the potential energy, gravitational potential energy, because when he goes down, then that would create an increase in his speed as he goes down the hill, which would then turn that into kinetic energy. This is the same as if it were at the top of a slide. So this is just showing you that, again, there is height, and because of this height, the object, either be it a cyclist, a person at the top of a slide, a book that is going to be dropping down, anything with height will create the possibility for kinetic energy. Nuclear energy is potential energy. It has the potential. It's stored in the nucleus of an atom. And some examples are fusion. fusion in the sun, which is where hydrogen fuses and produces helium, and then it also produces the nuclear energy as a byproduct. So a hydrogen bomb, for example, is the fusion of hydrogen atoms. Fission is the opposite. So instead of fusing, you're actually splitting, and you're splitting one atom into two atoms, which then produces a large amount of energy. This is what we were talking about for fusion. Fusion is where you have your hydrogens and then they're joined together, and by joining them together, it produces helium and a neutron and a helium. Nuclear fission, on the other hand, is where you're taking an atom, you're taking the nucleus, and you're breaking them, and then you're creating all of this large amount of energy. And here is a nuclear explosion, which is the fission of an atom. It is amazing how much power can be released from something so small that we cannot see. With all things, energy can be changed or transformed from one type to another, but you can never make new energy out of nothing, or you can't destroy any. So this is the law of conservation of energy. That means that the total amount of energy in the universe stays the same. When we're talking about energy transfer, we said that it can change from one into the other. For example, when a rocket is launched, we start off with chemical energy in the form of fossil fuels, and then it is turned into kinetic energy, which comes out as sound and as heat, or the thermal energy. And then from there, it also turns into gravitational energy. So there is a change from one energy into another. So it can happen, there is no loss of energy, everything is accounted for, it just changes into another form. With energy flow diagrams, which is what you saw from before, an energy flow diagram shows energy changes that occur in a given situation. So for example, when a car brakes, its kinetic energy is transformed into heat energy in the brakes. Down below here, it shows kinetic going into thermal. And so you're going to notice that there's an arrow that's showing what the starting energy form is and what it becomes at the end. Here we have an example of electricity, which starts off as chemical energy stored in a cell, which then is changed into electrical energy into the light bulb, which then turns into light energy and thermal energy. So that's where we get our light. Efficiency. Efficiency is a way to compare the total energy put into a system to how much useful energy is actually taken out. There is usually losses when you change from one source of energy into the other, and this could come from friction, which produces heat, and that could be a waste product. It could be elastic potential energy from springs. This applies to all energy transfers in any mechanical, electrical, or other type of transfer. The equation is efficiency equals the useful work out by the total work in, which then equals how much power out that can be used to how much power went in. For example, we have a Sankey diagram, and this is just pretty much a diagram that shows the magnitude. The arrows show the magnitude of how much energy is going into either the waste product or the part that is actually being useful. In this case, we're looking at a light bulb, and we're taking this particular light bulb, which has 500 joules of electrical energy, of which becomes a large amount, which is wasted energy in the form of heat. And this heat energy is saying that it is releasing 425 joules out of the 500 joules for waste energy as heat. And then there's this tiny little amount of 75 joules, which is released as light energy, which is useful. So when we're looking at this, we look at the efficiency and we take how much is useful to how much was the total amount that went in. And in this case, we have a 15% efficiency. Not very good. Here is another example, and you've probably seen this. Maybe you even have some in your house. And this is an energy efficient light bulb. When you look at the amount of energy that can be produced, how much is actually useful and how much is a waste, you can tell that this one has a higher efficiency than the last light bulb, which means you have a lot less waste. All right, so that's pretty much it. And be ready to use this information in class and rewatch the video if you're a little confused. Also check your textbook for more information to solidify on the content.